Okay, today I'm going to be doing problem number 7 in chapter 5. The problem reads, a sledge loaded with bricks has a total mass of 18 kilograms and is pulled at a constant speed by a rope inclined at a 20-degree angle above the horizontal. The sledge moves a distance of 20 meters on a horizontal surface. The coefficient of kinetic friction between the sledge and the surface is 0.5. A. What is the tension in the rope? B. How much work is being done by the rope on the sledge? And C. What is the mechanical energy lost due to friction? So to draw up the separate forces, so we have the force of friction pushing backwards, mg down and n up, and then the T1 at a 20-degree angle. So if we're going to solve for the x and y components of T1, considering this is a 20-degree angle, we can solve this as T1 sine 20 for the x component and T1 cosine 20 for the y component. With that information, as it's stated in the problem, considering it's being pushed at a constant speed, that means we know that the acceleration is 0 meters per second squared. We also know the total distance is 20 meters. So with this, we can write out our different sums of forces. So for forces of x, it would be the T1 cosine 20 T1 cosine 20 minus the force of friction, which would be equivalent to mass times acceleration, and then the sums of the y forces would be equivalent to the normal force plus T1 sine 20 minus mg, which would be equivalent to ma as well. And this would be the ma for x and ma for y. With this, as we know, considering it's being pushed at a constant rate and an acceleration for both is 0, both sides equal 0 and as 0 cancel out. So for the sum of forces of x, you can simplify that down to T1 cosine 20 being equivalent to f of fr, and also n plus T1 sine 20 be equivalent to mg. Knowing that the force of friction is will be equivalent to mu n, and if we isolate n in this equation to n equals mg minus T1 sine 20, from here we're going to start plugging in some of our information. We're going to do n equals 18 times 9.8 minus T1 sine 20, which would equivalent to n equals 176.4 n being newtons minus T1 sine 20. Then we can plug in n into the other equation to result in T1 cosine 20. And considering force of friction equals mu n, we'll plug in mu n for force of friction here. So, and then we'll plug in n for the value we got here. So that would result in T1 cosine 20 being equivalent to mu times 176.4 minus T1 sine 20. After that, we're going to plug in the value of mu, which is T1 cosine 20 equals 0.5 times 176.4 minus T1 sine 20. After that, what we're going to do is we're going to multiply each side by 2 to take away the 0.5 here. So it would be 2T1 cosine 20 equals 176.4 minus T1 sine 20. So then, if we want, then we're going to isolate the T1 to solve for it. So that means 2T1 cosine 20 plus T1 sine 20 equals 176.4. After that, we're going to isolate T1 by bringing it out of this by dividing it out of here, and then dividing each side by the what's remaining, so that would be equivalent to T1 equals 176.4 over 2 cosine 20 plus sine 20. Okay, and then we can solve for T1, and T1 is equivalent to 79.4 newtons. So that's our answer for part A. Part B and C are a bit easier from here, not as much, like that was like the main set of work to solve for the system of equations. For B, it would be knowing that work equals force delta x cosine theta, we can plug in our values. So W equals 79.4 times 20, which is the 20 meters, and then cosine of 20, and this would give us a work of about 149.2, 1,492.23 joules. That's our answer for part B of the work of the tension of the rope. And then for part C, it is also, we're going to bring back the equation W equals F delta X cosine theta. So work equals 79.4. Also, actually, we're not going to do that actually. What we're going to do is, we're going to also take into account that the force of friction equals mu n, and with that n equals mg, and also we're going to get the equation of n equals mg minus t1 sine theta that we got in part A of this question, and then we're going to plug in n equals 18 times 9.8 minus 79.4 sine theta, because now we have the value for T1, so we can plug that in. So we got it from part A, and then it would result in a normal force of 149.24 newtons. While that's the final normal force we got, we're solving for and then we're going to plug that in, solve for the force of friction, and that would be equivalent to 74.62 newtons. While that is the force of friction, we're solving specifically for the work of friction in this equation. So we would plug it into the W equals F delta X cosine theta. So W equals 74.62 times negative 20, because the delta X is going in the direction opposite to the force of friction, cosine theta, and then that would give you a final answer of 1,492.4 joules. That's the solution for question number 7 on the homework for chapter 5. Thank you.